Hi everyone, we are going to continue our lecture on the hierarchical clustering, and we are going to revisit some of the linkages we talked about earlier. So, well, if we use those three clusters as an example, and let's assume that those three clusters have already been merged. Okay, so if we want to do one more step and merge another two of them, and which one should we merge? So there are two statements. So the first one is in single linkage cluster 3 and is closest to cluster 2. And the statement B is in complete linkage cluster 1 is the closest to cluster 2. So take a look on this graph, and if you need to, you can pause the video and revisit the definition of the complete linkage and the single linkage. So tell me your answer. Which one, which, well, 1, 2, 3, 4, which one do you think is true? The answer should be 4. So number 4, both A and B are true. Uh, excuse me. If you're using the single linkage, so for the single linkage, we are picking the closest two samples between two clusters, and that will be the definition of the distance. So if we are doing the single linkage, and then the distance between cluster 2 and 3 will be determined by those two samples, right? So, and then if you're checking the single linkage between cluster 1 and 2, and that will be defined by this distance. So it seems that, well, if you only take the samples which are closest to each other, and then cluster 2 this sample and cluster 3 this sample, they are the closest. So if we're using the single linkage, we will merge the cluster 2 and 3. And if we're doing the complete linkage, for the complete linkage, we have to get all the distances between all the samples of those two clusters, right? So like if you're doing the distance between cluster 1 and cluster 2, and then we do have to pair each two of those two samples together. So there are a total of 4 distances between cluster 1 and cluster 2, and then I'm going to take the average. And the same thing here. There are 2 samples in cluster 2 and 3 samples in cluster 3. So to get the complete linkage, we are going to get a total of 6 distances between all the samples in cluster 2 and the cluster 3, and then we are going to do the average. So in this case, on average, we find that for the distances between all the samples in cluster 1 and cluster 2, the average will be lower. So in this case, for if you're doing the complete linkage, and then we are going to merge cluster 1 and cluster 2. Okay, so why do we bother to talk about the different linkages? Because later, if we have decided that we want to use a hierarchical clustering, we do have to specify what is the linkage we have to use, and then there has to be a reasoning behind the scene. And otherwise, if I just randomly pick one, and I could be wrong, and later we are going to see example. Okay, so we also want to talk about the time complexity. And if we are trying to cluster a very small data set, those are the cities in Italy, and then we are going to build a n by n distance matrix first, right? So though there are only a total of 6 cities, so we build a 6 by 6 matrix, and well, for each of the value in the cell, and that is the distance between city A to city B. Okay, so if we want to find the closest two cities we want to merge, and then the lowest value, the lowest non-zero value I see is this one, 138, right? So that is between TO and IMI. So TO and IMI, they are here. So if you want to merge those two cities, and I do have to rebuild the distance matrix. So now I have a new line and new column called IMI-TO. So those two cities, they have been merged. And after that, what is the distance between the cluster IMI-TO to BA? Well, to answer this question, you have to tell me what is the linkage we are using, right? So since let's just assume that we have already decided a linkage we are going to use, and then we only need to update this column and this row, and so we can continue. So in the next round, we are going to pick another lowest value, which is the BA to NA, and then we merge them together. And after that, we update another row, another column. So it seems that we are constantly merging the two samples, and then we have to update this distance matrix, right? So does that sound a little bit computational expensive to you? Let me just give you the answer. The answer is, well, the time complexity of the hierarchical clustering is OM cube. What does that mean? Well, if you still remember the time complexity of the k-means, we say usually we consider k-means as a linear time algorithm, right? And then how about db-scan? For the db-scan, usually we say that it is square time algorithm. And how about hierarchical clustering? Hierarchical clustering is a cube time clustering algorithm. So the important thing you want to remember is hierarchical clustering doesn't scale very well with a large data set. So if you have a large data set with thousands of samples, then probably hierarchical clustering is not the clustering algorithm you want to choose. So it seems that hierarchical clustering is not that useful. So why do we still want to do that? And there's one really cool thing about hierarchical clustering. That is, we can generate a dendrogram, and by creating a dendrogram, and we can visually have some sense of this data. Or if you are clustering a very small data set, and then you want to show the clustering process to a non-technical person, and then dendrogram is another very handy tool that you should use. So I know we have been using scikit-learn for a very long time, but this time I want to use the SciPy. Why? Because SciPy provides us the dendrogram, and that is exactly what we will need. Okay, and then we also have the linkage. So we are going to do everything with SciPy in this lecture. So we have a dataset, and that is a wheat dataset, and we have a total of 3 different species of the wheat. Okay, and then for each of the sample, we have a total of 7 features. Okay, so the first thing we want to do is we want to create a linkage. So this is a SciPy function. It's not a scikit-learn function. So we want to send the samples, and then we specify the method as complete. So in this case, we are creating a complete linkage. And after that, we create a dendrogram, and then well, we rotate the leaves. So as you can see, the labels, they are all rotated 90 degrees. And then we also specify the leaf font size, and then we got this dendrogram. So in this dendrogram, you can see we have a green cluster, a red cluster, and then a blue cluster. And for each of the sample, and we can see clearly how they are merged together, right? So say if we do take those 2 samples, and those 2 samples are merged here, and they are merged on a very low distance. And then if we move on, and then those 2 samples, this cluster is merged with this sample, okay, on this distance. So the y-axis is the distance, and then it determines when a merge will happen. Okay, so here is the time that we have one cluster and another cluster merged together as one cluster. And then if we move on here, so at 5.5 roughly, and then we have 2 green clusters merged together into a big green cluster. Okay, so well, did we really have the clustering results? No. Well, because eventually everything will be merged together. This means if we specify the acceptable distance between the clusters as 10, and then eventually all the samples will be merged together into a huge cluster. Well, say if we want to cut the threshold here at 9, So if you want to cut here at 9, and then what will happen? So if we specify that we are going to allow the distance, the max distance, to be 9 and then not beyond 9, and then we will have one cluster, that is the green cluster, and then for the red cluster and the blue cluster, they will be combined together into one cluster, right? So in this dendrogram, we didn't have samples clusters. However, uh, we will have the sense on how those samples, how different those samples are, or what's the distance between different clusters. Okay, so mm, let me see. Well, if you want to stop the height at the height 6, and then what are we gonna have? So if you want to cut the threshold at 6, which is here, and if you draw a line here, you will see there are 3 clusters, right? So after this means after doing the dendrogram, and then we want to decide 6 might be a good threshold. So we are going to merge all the subclusters into bigger clusters, but we want to stop after the distances are beyond 6. So we will have 3 beautiful clusters. So they are beautiful, but they are not perfectly beautiful. Especially here, we have comma vid, and then Canadian vid. So we have 3 comma vid got mixed together into the Canadian vid. But overall speaking, we are doing fine. Okay, and another thing, if there are 3 samples, then how many merges do we have to do before we merge that into one cluster? So 5 samples. And then how many merges do we have to do before we have only one cluster? Think about that. The answer should be 4, because after each merge, we will reduce the total number of the small clusters by 1. So to begin with, we have 5 samples, and we can consider those 5 samples as 5 mini clusters. Okay, so after one merge, we will have 4. Okay, so each merge, we will reduce the number of the clusters by 1. So we reduce from 5 to 1. So there are a total of 4 clusters we have to do. Okay, so I think that's it for this video, and I'm going to continue in the next one.